Happy Tuesday afternoon. My name is Tom Lowell. I'm ostensibly the instructor for a course called Global Warming, and it's got some code number that I don't remember. This is section 1. This is one of 2 sections. This is a course that this year will be offered as a face-to-face, which you folks are doing, and will also be offered online asynchronously. Therefore, as Liz says, we're going to be recording this, and that will be available to you also if you need to make up and you have some reason you can't come to lecture or need to review things. That information will be available. Liz is also currently posting the lecture notes, which will be as a separate PDF, because we're not sure the video will give you all the detail that you might want on some of the graphs. Okay? So again, my name's Tom Lowell. I'm professor of geology here at the University of Cincinnati, have been for way too long. And my interest is glacial geology. I look at glacier systems. I try to understand how they work and how their patterns in time and space. That's directly related to climate. Glaciers are sort of the simplest thing we can track climate with. They melt when it gets warm and they grow when it gets cold in round numbers. And therefore, I have some insight to this course called Global Warming. I've been teaching it way too long. It's never the same any 2 years. The reason it's never the same is the topic's never the same. When I started teaching this course, there was a continuous debate whether the planet was indeed warming. That debate's over, despite whatever else you might hear. The challenge facing you folks is not whether the planet's going to warm up, it's how we're going to do it. I can't offer you much advice on that. What I can offer you is the opportunity in this class to look at the geologic history when global warming events have happened in the past and how things have responded. Things like the water balance, things like the biota, things like sea level. All of those things you've heard about in the news, you've probably been drilled in your head, you're probably tired of it, but you can't be too tired because you're here in this class. Again, so what I'm going to try to take you through is a story about what's happened in the past, because there are lessons there. And those are the things that I can provide to you. We're going to deal with the first lessons a little bit more about the climate sensitivity than the rest of it, but that's climate sensitivity is a metric that we're talking about. Before I go any further, any questions or comments or suggestions? Okay. Who are we? Tom Lowell. Elizabeth, you want to say something about yourself, please?
Hi everyone. I'm a second-year master's student here at UC. I study petrology, which is basically rocks that are very, very tiny. And my specific area of study is actually crystal systems, and right now I'm studying fluorescence and diamonds, which is kind of cool. So if you have any questions, please feel free to grab me. I'm happy to help however I can. And my contact information is on the syllabus. If you want to meet after classes, just shoot me an email and we can set up an appointment.
I'm going to randomly pick a couple folks, and if you don't want to contribute, I'd like to know a little bit about why you're in the class so I can better suit your need. So for example, I'm randomly picking on you first. Why are you here? What do you want to get out of this?
I needed to take a science course, my advisor told me, and I kind of picked this one just because I thought global warming was interesting and I don't know much about it, and it's pretty relevant right now.
Okay. The lady sitting next to Liz, can you give me why you might be interested and what we can do to help you? I can't quite hear you, sorry.
It's a really relevant topic right now, so I'm just interested in learning right
Okay. The gentleman on the end.
I chose it as well because I have to take the natural science requirement. But when I was
Have to,
going
my
through
God,
this-
it's onerous, right? Yeah.
I was scrolling through and saw this class, and again, just because it's relevant and you see a lot of it in the media today,
Okay.
I thought it'd be interesting to learn more about.
Anybody want to volunteer? I like dialogue. You will be asked to participate in dialogue. That will be missing from the video, obviously, for other folks, but that's part of the discussion. So what is this class about? Lessons from the past, history. What is the saying? Those who do not understand history need to repeat it. The geologic history is a little more nuanced than the societal history. I will walk you through those tools, techniques, the ways we get at things. I will try to make it more about learning something or setting a pattern for learning about something or making decisions. It's not a factual course. There will be a bunch of facts we'll deal with, and then I'd like to do something with those facts. I think of a learning exercise as more, I give you a set of relationships and we build on that. Take the exercise of building on the relationships more than worrying about giving more factoids. What is expected of you, the way the course is designed, it's a little bit every day. That will be great for some of you, it will be less great for others. I haven't given an exam in this course in more years than you've been alive, and I'm not going to start this year. The basic concept, I think, is if we just digest a little bit every day, we'll gain something. And the way we broke it up, it's into sort of 3 modules or 3 lectures per topic. And there's a success progression of basic information exposure, and then a little more synthesis, and then finally reaching some conclusions. This is not a give me A class. There's no way, though, if you do every exercise on time and with some sort of effort, you're going to get less than a B+. It'll take a little effort to get over the B+ grade, but not so much. Part of the exercise is feedback. By having little questions, lots of them, we have a lot of opportunity to give you feedback. And so we'll be not grading as rigorously at the beginning as we will at the end, but that's the way it works. All right, so where do we start? I don't know what that means. We'll start in a minute. This particular lecture is the most technical of the semester. So we're going to bear it a little bit, and it'll get a lot better. It's technical because there's a bunch of physics in it. I'm not trying to kill you off with the physics, but there's generally an attrition rate after the first day, so that's happening. Overall lesson that I'd like to get across to this class for the term, and I'll hammer it again, but I'm going to say it right now. The climate system is less simple than most people think. At the present time, there's the ad campaigns, the notion of trying to figure out what to do about climate change is housed on the assumption that we might be able to manage climate by managing CO2. There's reasons for that. CO2 is a greenhouse gas is a bunch of emissions, blah, 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 blah. They're probably, in my view, wrong. The Earth system does not behave in a simple fashion. If it was a linear system, it would be 1 to 1 to 1 to 1. With a little CO2 in, the temperature goes up. With a little more CO2, the temperature goes up. The problem is, from my experience, and examples that I present to you, the climate system is more of a working back, like a camera, straw to go back. And push it a little bit, there's nothing, push it a little bit, and then all of a sudden it does a lot. It's a threshold system, it's a chaotic system, and we have a lot of terms for it. But a system that's not as predictable as you're probably led to believe is less pleasant to deal with. So that's my, I'm not trying to be doom and gloomy about it, this is just my professional opinion. You can take it for what it's worth. Climate sensitivity that we're going to study today assumes a linear system, so I'm actually sort of giving you a tool that we use to make predictions about the future. It's the way all the predictions you've probably seen about the future are used. And then I'm going to say, well, maybe it doesn't work. So there's a contradiction, but let's be aware of that. Please interrupt if there's any questions. Global warming is about energy. The energy coming in and out of the system. It's the energy distribution. Temperature is changing, and that's what you think of as global warming, because warming is in the title. But we really need to think about energy balance. And the problem with the Earth, not the problem, the challenge and uniqueness of the Earth, is that it's a round sphere hanging in space that gets energy from the sun, and it moves that energy around in two fluids. One's called the atmosphere, one's called the ocean. And if you've ever stirred a cup of coffee and poured the cream in it and saw all of the convoluted things, that's what the atmosphere and the oceans look like. And so if we think we can predict what two fluids that are interfacing can do, the Earth's history, though, is a result of all that. So we can see those interactions have taken place. The real lesson that I want to try to get home, and I know it's not as tight right yet in the past years, not as tight as I want to make it this year, is what happened because of that. Global warming may have made up is interesting as itself. I've been studying it for a long time, various time scales. But what happens to the things like what happens to the things like water levels? That's what we need to go. So those are the examples we want to talk about. And I will maintain that one of the big revelations or rethinking of science in the last few decades has been the advent of computers and computer modeling. In other words, we can articulate with mathematical formulas how things should work. And we've learned an awful lot about the universe because of modeling exercises. The modeling exercises that we currently use to predict future climate cannot replicate past climate. They're not sophisticated enough, they're not designed with the right philosophy or whatever. As a skeptic, you can say, well, if they can't replicate the past, then how good are they for the future? They're a lot better than nothing. Are they absolute? And so what are the key lessons? That's what we want to worry about. The lessons are something about climate variable sensitivity today. That's a metric that gives us an excuse to deal with some physics behind it, just to give you some versatility in, excuse me, this is a phone that's cheating to find out what time it is, so I'm just going to step up there once in a while, okay? And then we're going to hydrological patterns. You're seeing some interesting hydrological patterns, hurricanes in California, drought in California, storms in California, blah, blah, blah. All of those things are, the example we'll use is several thousand years old, but it basically, the Great Lakes that you know and love, they weren't as great back then. In fact, they were closed. There wasn't any water running out of them several thousand years ago. There were folks harvesting the caribou as they walked across what is the bottom of the Lake Huron today. The AMOC, you may have seen that set of terms, is the Atlantic Mediterranean, not pronouncing right, ocean circulation pattern. It's basically the Gulf Stream is part of that. It's the large-scale pattern of how the ocean works. There's been a lot of discussion about using salt water, the thermohaline circulation, which is both temperature and salinity, can be disrupted if you pour fresh water in it. That disruption has the potential turning on and off things like the Gulf of Mexico are pretty serious. It's the basis of the movie The Day After Tomorrow, if you ever saw that years ago. Ecological reorganizations, a lot of the climate changes that we deal with in the last 20,000 years have also been accompanied by significant ecological reorganizations. Higher forest types become no. There's something called the no modern analog. There's a forest configuration that was occurring here in the Midwest something about 13,000 years ago. There's no place on Earth that looks like that. The tree species are mixed in a way that they aren't anywhere today. We'll talk about sea level, the notion of you want to build a new structure sort of a meter or two above sea level, you want to have good flood insurance. We'll see that the sea level is quite a bit in the past more dramatic than we're anticipating. The marine ice sheet instability hypothesis is too many words, but it basically means that ice there's mechanisms that we currently understand that would allow this one to happen at a much faster rate. If you want to change sea level, you've got to take the ice from the polar ice sheets and move it into the ocean. You can do that by melting it because it gets warm, or you can take whole hunks of it and let it flow out into the ocean and break up into little pieces. This one works much faster. We'll talk about long CO2. The notion that we've been introducing CO2 levels, they're now higher than they've been for, I don't know, it depends on who you read, but it's millions of years. And the real problem is if we actually stop CO2 tomorrow, which is impossible, the CO2 levels wouldn't go down. I mean, CO2 has part of the natural cycle. It is absorbed into the ocean. It'll take 100,000 years to get reabsorbed into the ocean. So the CO2 levels that were present the year you were born will never be seen again for at least 100,000 years. Does that matter? I don't know. And then my favorite, abrupt climate changes or rapid climate changes, which are the type section of this nonlinear behavior. And that's what we'll wrap up the class with. Those are the topics. Ask, respond if I ask you questions. Please interrupt me. It's not an interruption, but ask questions. In the homework, do a little bit, do it all, do it every time. You'll be fine. When we provide that feedback, and it's a pain for us to do that, you'll do it in a cursory form, but we also expect that if you don't understand the feedback, you ask us so we can explain it. We'll probably use a fairly simplistic grading system that says, this isn't really good, this is okay, this is solid, or this is exemplary. Rather, we're not going to call it 5.2 points. We're going to say, you got a point because you did something, that you really need to rethink this, or you get 5 points because you really nailed it, or you're in good shape. You'll get feedback every day, hone your skills, and then that will lead to your increased knowledge. Okay? Let's go. You think we're still recording? Syllabus should be online. Where is it now?
It is online, it's under the syllabus tab in Canvas, but it's also in the files tab.
And I think I sent everybody an email with it this morning, so you should have the syllabus. You can see the layout, the scheduling of what's there or not. As I said, each lesson will be 3 days long. First day I'm going to introduce the topic, which is background terms, concepts. We'll do a little analysis by hooks, different techniques. Some of them will be mathematical, make you cringe, but it'll be algebra, so it won't kill you. And then we'll really think about, well, what does that mean to me on the third day? And then we'll move on to the next one. So this is, I'm not going to stand up here and lecture at you. I cannot lecture you to do analysis of principles. I can guide you. I can give you exercises that will get you there. And I can evaluate how well you're getting there. That's my job. Not to fill you full of a bunch of facts. Or opinions. Or shit. All right, that looks like it's a cumulative points. There's 800 points that you could earn. There's a breakdown of where you need to get an A and whatever. And usually people don't quite translate that easily, but nobody has any points right now. So nobody's getting an A today. And in the past, people have figured out if I get whatever the threshold is to get an A, there's no reason for me to come to class, and that's fine by me. So, we'll accumulate points, you won't get out of too many classes that way. Blah, 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 800, so each of these are 100 points apiece. Okay, the missing work, we need to be advised before. We understand things come up on suddenly. There was a person that had a pretty serious set of migraines already. So as long as we're advised ahead, we'll work something out, no problem with that. But please let us know like a couple hours before it's due so we can adjust it. All right. Let's get through the administrative stuff before we jump into the technical stuff. Are we through with the administrative stuff? Gentleman right there, any questions? It makes perfect sense, some sense? Think you can deal with it? Lady with the black drink shirt, yeah, wait, all right? No questions? All right, why is there air? You should ask why there's air. Technical stuff, it's the worst technical lecture of this whole semester. I'm going to show you a couple technical papers or just the headings of them. They're going to have a bunch of fancy jargon words with them. I'm going to break it down to you that things break. There's climate, something called a system, which is a bunch of interacting parts. It's a different type of analysis. You probably take some, if you're in business, you'll probably take something on operational systems or some kind of systems course, because systems are a bunch of things that work together or work apart or work in different dynamics and but they're related onto each other. Most systems have a fairly complex behavior. Some are unpredictable. A subset of all of them are unpredictable. Climate's in that subset. It doesn't seem to respond in one way, which is starting to sound like an old song now, and we'll give you examples of that. All right, promised nonlinear dynamical systems, of which climate is one. First statements, the first is the critical thing. It's an operational definition. If you ever had to throw that up on a test, that would be the right definition. What does it mean in English? Dynamical systems are those or that describe how over time, change of state, and that's conditions. So one of the things, properties of state is temperature, for example. One of the things of the change of state, we could have, many of you know there wasn't classes here before this one, and so the state of this class had a certain coolness to it. Now that I'm in here dancing around and all you folks are sitting here, the room is changing its temperature because the state is changing. We all leave it and calm down, cool down a bit. But the state, that's what they mean, the state variable in time, the fact that there was no temperature, then there was temperature, and then it's going back down, that's kind of describes the system. These systems, and we call them, they can be done with equations, differential equations, which we don't want to know. Research in nonlinear dynamical systems in particular is interested in the quantitative state system. This is a working definition. I couldn't expect you to repeat it. The word chaos is in it. Bifurcations mean they can go one of two ways. So it's not predictable. Chaos is an expression. It used to be chaos theory. Now chaos is an accepted behavior. That means that that's the flapping of the butterfly wings in Brazil impacting a hurricane. Initial conditions, a guy named Lorentz discovered this back in the 60s. He was running a computer simulation. And he found that if you change the conditions just a little bit, you get a totally different result. In other words, he went through his mumbo jumbo with his computer and he got an answer of 6.3. He started with 4 or 5 variables and they all had a set number. But if, in that days, because the computer couldn't represent the number very well, you changed the number, you go from 6.3 to 27 or something, making the numbers up. But the point was he couldn't predict what was going to happen from the initial conditions. And that's what these nonlinear systems are. The way you want to think about it is we can push something push something, it doesn't change much, and then it breaks the back. That's a bifurcation point technically. Okay? Questions on that? The other paper that we talk about is something called punctuated equilibrium, which is sort of the notion that things will go happily and every once in a while we'll change our equilibrium status. It's sort of this, for our purposes, it's the same concept. As academic levels, they'd argue a little bit, but for our purposes, it's the same thing. This is used a lot in evolution. We have a certain set of fossils going along, and then all of a sudden something happens and they change assemblages. Well, what this paper does, this is just the heading of the paper, is it talks about the last 65 million years, that's the geologic time. And then look, it says we have abrupt transitions, and they have a structure to them. There's little ones, medium-sized ones, and big ones. And they go through this, they do a mathematical analysis that's way too messy to even show. But this interprets the time evolution as a trajectory taking place on the dynamic system. Back to the point I'm trying to synthesize here. Describe a hierarchy of metastable states and associated tipping points. Tipping point's the other word. Going along, tips over. So the tipping point, breaking the back, nonlinear systems, for our purposes, they're all kind of the same concept. Just means it's not so easy to predict. The Earth's history is experienced, he said this in the published paper. I came up with the idea before he did, but, or these folks. I guess it's a he. Experienced numerical critical things in its history which have often been accompanied by massive and rapid changes in the biosphere, which we're part of. All right. To illustrate that, they drew a nice little cartoon here. I don't expect the details to come out, but basically what this is on the time axis is way back in the geologic past, 65 million years, the future. And the vertical axis has something to do with some approximation of temperature. If you go back this many million years, the continents had a different configuration than they do today. So that means different ocean circulation patterns. So one of the big things that happened is that you broke up South America from Antarctica. So all of a sudden there's a passage all around the Antarctic current, around the Antarctic continent, excuse me. And that happened in certain millions of years ago. The point is that we started here with a high CO2, it got hot. This was the maximum times CO2, this is the millions of years ago when their highest were present. We come down, we change the continent configurations, it starts cooling the planet. The planet for 34 million years gets cooler, ice sheets in both polar hemispheres, for one. They have a pattern to them. And then what we see are the ice ages get more extensive. And when we get down to sort of this time frame, we talk about the ice age that's impacted Cincinnati. So this is, the point is, it's a long evolution of things where there's abrupt, many changes in it. And according to this, with the CO2 rising, we're going to go back into a new set of conditions. This was a set of conditions. This is a set of conditions. Ice, they call them hothouse and warmhouse worlds, ice house worlds. And then they're going to call this, I think, the Anthropocene or something. Don't need to know those details, just that again, my point, they're there. So it's not me that's making these up. All right, now I want to give some operational definitions for things like these terms. Energy balance is going to be basically that the energy coming in and going out of the system has to be equal. We're going to talk about radiation as one way to move energy because it's the most effective. And then we're going to talk, that will allow us to talk about the greenhouse effect that will need to have atmospheric windows. And then that will get us to climate sensitivity. So there's like about several slides of each of these concepts, well, not several, but just 2 to 3 slides of each of these concepts. So we're just going to bludgeon through it. Basic principle. The world, there's a lot of thermodynamics. The energy, if you put into a system, has got to stay there, or it's got to be output. It can't just accumulate energy. It likes to dissipate. It's called entropy. For us, for the Earth, the energy in is the sun. You're all probably aware that the center of the Earth is quite warm. Once in a while it burps and it throws up kimberlites and you get diamonds or something like that. But the reality is the energy from the center of the planet doesn't do anything to us on a day-to-day basis. It's all from the sun. The heat doesn't pile up here. It can't because of the thermodynamics. It goes back out into space. Comes here, hangs out for a while, disappears into space. The yin and yang have to be in sync on a longer time scale. They don't have to be instantaneously in sync. Therefore, the total energy on the, and they're not. They would be if we didn't have oceans, those fluids, oceans in the atmosphere. If we had a dull rock, it would be a lot simpler climate. Wouldn't have life, but it would be a simpler climate. With those fluids, though, they're moving energy around. Gulf Stream moves a lot of energy from the lower latitudes near the tropics and the equator up to the North Pole, towards the North Pole. It doesn't get that far. The atmosphere has a series of ways it also likes to move energy around. But they'll balance out. A hidden assumption here is we can balance out at different energy levels. We have a lot of energy and we can be in balance. We can heat the planet up and be in balance. We can cool the planet down and be in balance. Those are the ice ages. We were in balance though, then they went away. So something happened. So they're in transition, but they still have to be in balance. The two fluids things are starting to get a little boring probably to hear, but we would use them as a technical term called fluxes. Energy has to be a flux. We have to have amount per time. Okay? So far, so good. Now let's bludgeon on. It's a diagram. This is part of a diagram. You'll see the complete one later of the energy fluxes coming in and going out of the planet. Basically, it's all sun coming in. Here's a number to prove that it's there. It's watts per square meter. It's the old incandescent light bulbs. It's about 3 of them showing, shining on the size of the table in front of you. That's how much energy comes in every square meter of the planet. The planet has an awful lot of square meters. Some of it just bounces right back out. A third of it bounces back out. The rest of it goes into the convoluted system and comes out later in round numbers. So the energy, if you add those up, the energy's in balance. Watts per square meter, common. It's a unit I need to introduce you to because there'll be some descriptions that we'll talk about a little bit about that. And here's the best one. But think about it, 300 of them, so that's 300 light bulbs shining on that desk. Pretty warm. That's on average. The sun does a lot for us. We throw a third of it back. The other 2/3 go around and around and around and come back up. This is something called, this concept is called the black body radiation. Radiation is an effective way to move energy from one point to another. This is a theoretical concept. It's not real. It's a way to describe energy. And basically what the black body theory, or theorem, or concept is, if you have an object floating out in the vastness of space all by itself, if it has any energy, it will radiate that energy. It doesn't want it. It's not in balance. It's entropy. If it accumulates energy, it'll spit it out with radiation. And that's fine. Temperature of an ideal object, black body, it's a conceptual idea. It's called black because I don't want to give it color. And the radiation it emits. So the black body conceptually could be this remote control, And if the energy that's in this is in part radiating a little heat from the battery that's, connected to it. If I wanted to calculate how much energy, the R, it's an equation of that form. And there's a fancy number, temperature to the fourth power. Now, temperature to the fourth power means temperature times temperature times temperature times temperature. So that's a very, very sensitive. There's very few physical constants on the planet Earth that are to the fourth power. And what this says is that a little bit of temperature change really makes a difference in the amount of radiation we get spitting off from the black body. Raise it just a little bit, and it's a little bit times itself 4 times, that becomes real numbers. And so, and this isn't the Kelvin scale, which is the Celsius scale, but that's okay. We don't want to get too far. I'm not going to have you calculate those. The take-home point is it's the fourth power. The other thing is, what we haven't talked about, the next concept is it sends that energy out in what we call a wavelength. You're used to visible light. Light is energy transfer. You know that the light is made up of different wavelength colors. Each one of those colors has a different amount of energy associated with it. When we talk about the wavelength of longer and cooler and shorter, hotter and shorter. So if something gets hot, it's going to give off short waves. If something's lukewarm, it's going to give off long waves. Okay, we're going to convert this as the sun is hot, way hot compared to us. It gives off little shorty waves. The Earth has heat too. It gives off long waves because it's a lot cooler than the sun. I'm going to show this in a graph in a minute. This is the basis of the greenhouse effect, because it turns out that the 2 graphs we had, the energy coming in from the hot source and coming back out of the ocean, out of the Earth, much cooler, has a different wavelength. Oh, that's neat. But we're going to have a window for that energy to get through. That will be the atmospheric gases in a minute. But before that, let's look at a pretty picture. What I want you to get away from this graph is this. This is some metric of energy. This is this wavelength property. These are long, these are long, these are short. Here's where visible light falls on this graph. Red, infrared, longer and longer wavelengths. Violet, ultraviolet, and shorter wavelengths, higher energy. And nice pretty green colors which plants use for chlorophyll. So in this graph, we encapsulate this sunlight. And the other thing that's shown on this graph are these curves, and there's 4 of them, and each of them have got a number with them. And it's the temperature of that black body. 7,000 degrees, 6,000 degrees, 5,000 degrees, 3,000 degrees. What you see is, boy, there's some difference between the whole area or energy at 3 and 6,000, because it's times 4 times 4 times 4. The 300 Kelvin is, 500 Kelvin is, excuse me, the sun's about in here someplace. That's why we get these colors out of the sun. The other thing that is important, besides the size of the peak, is this business. The peak moves from here to here to here as you get hotter temperatures. That's going to control the energy getting out of this system. Got to have a question on that? Got a question on that? No, it was you. No. It'll take me a long time to read the names. And if we need to, I'll develop a system to call on you randomly, but we'll see how that goes. So that's fine. We've got energy. We're going to get rid of it by radiation. Radiation has a physical property that says it has a systematic thing to it. It's really sensitive. All right, let's do this. Let's talk about the greenhouse effect. The greenhouse effect is exactly this. It's something that prevents the energy from leaving the Earth. If we didn't have an atmosphere, all that energy would come in, warm up the dead, cold rock of Earth, and then it would re-radiate that energy out at some lower temperature. But we have an atmosphere. It has gas in it. Those gases can hinder that energy from going out. Why? The molecules of the gas are the right size, but they interfere with the wavelengths. Different gases have different molecule sizes, they interfere with different wavelengths. Incoming, shorter, we got that. Outgoing from the Earth, longer, we got that. The atmosphere doesn't transmit all wavelengths equally because there's gases in it. The energy is blocked. It keeps the planet warmer than it would be without the atmosphere, about 50 or 60 degrees Celsius. If we didn't have the greenhouse effect, there probably wouldn't be life on this planet. Well, life is so maybe more ubiquitous, but you would not have liquid water on this planet. Let's put it that way. It might be if you wait. So the greenhouse effect is a natural good thing, blah, blah. When does it become a bad thing? When you start perturbating it. Can the energy be in balance at play? Surely. The greenhouse effect warms it up, so a warmer thing gives off more energy. It gets rid of it. So a cold Earth is going to give off that much energy, a warm Earth will give off that much more, keeps it in balance. That's the regulator. The greenhouse effect keeps the energy in, the black body radiation allows it to escape because it's warm. We warm up the temperature of the planet 5 degrees, going to give more energy off. Not much, but enough. Okay? Good for that. You good on that, sir?
I think so.
Well, no, you have to tell me if you're good or not, right? And that's why I'm asking.
I always assumed that the greenhouse effect was more of the chemicals in the air, in the atmosphere were increasing how effective the sun was, not that it was trapping the heat. Kind of like a magnifying glass.
The sun is giving us any energy, that's fine. The energy can't accumulate, so it's going to go back. Fine. The atmosphere, though, is basically transparent, or those short waves from the sun go zooming through. They don't care. Some of them bounce off. We saw a third of them bounce off. The gas in the atmosphere, the molecules of the different gases, and there's more than one greenhouse gas, prevent them from just zipping out, the longer waves from zipping out, because those longer waves, the molecules in the gases have a tendency to block the longer waves from going up, so they trap the energy and they re-radiate. I think that's a little more, what you had has a concept there, have a basis, but I think it's a little skewed. Okay, is that better?
Yeah.
All right. And what to do this, though, what we want to do is the next definition have, well, here we go. Here's the windows. Yellow is the energy coming in. If you held a fancy satellite up at the top of the atmosphere, and they've done this is where the heat comes from, you get sunlight coming in, and it has a tapering thing with these longer wavelengths. And this is about 5,000 degrees Celsius, one of those curves that we saw. So this is the energy that wants to bombard the Earth. That's at a certain wavelength, because the temperature of the sun is a certain temperature. It's not one wavelength, it's a distribution of wavelengths. That's fine. If you went to space, though, and you turned that sensor around, instead of looking at the sun, and you looked at the energy coming back up, it looks like the red line. And the red line is generally lower than the yellow line. That's the trapped energy. There's also one other thing. There are particular dips in the red line. Why are there red dips? They're associated with H2O, as you see there. And they're associated with H2O because that's the size of the H2O molecule, so that prevents anything from getting through. There's none of this energy going back out of the system. This area, that area, that area, that area is trapped in there to warm up the planet. That's the natural greenhouse effect. So those two graphs of different energy systems tell us 90% of what we need to know about energy. Okay, I'm going to show it in a simplified diagram in below. But these are the windows. And is window maybe the best term? Lady with the white hat. Is a window the right way to talk about this?
Because, you're saying it gets absorbed and it doesn't come back out.
It can't get back
I mean,
out.
you can see through a window, so I don't know.
So it seems it's kind of the wrong term,
Yeah.
isn't it? Yeah, exactly. So these are where it's blocked. These windows are actually the opaque parts of the atmosphere. There's an overall opaqueness, but then there's specific opaquenesses. Okay. So yeah, so windows is, that's why I put, you see the windows a lot, but I put blocks up there for that reason. Okay, same diagram, or similar diagram. Sun along with the Earth light, Earth radiation. Some of it comes in, some of it bounces out instantly. Because the white, there's white and there's reflective surfaces. But there is the energy, and the scale has changed on us. It's logarithmic now, so those two curves get separated. Here's Earth's longer wavelength, giving off energy. But because of the non-windows or anti-windows, some of it's bounced back down. It's a pretty small percentage, actually. But it's enough. It's enough to keep us warm. So there's the same basic principle as the last graph. The other one's a little more technical, but I think I put this one up because it shows it a little bit better. Reinforces it. If you wanted to do it more complex, before you saw just these going in and that what's coming out. The reality is that some of this goes right back out, some of it gets into the atmosphere, some of it gets into here, and then this is the re-radiation, but the cloud, the atmosphere, the gases get in the way, send some of it back, bounces it around. I don't care that you necessarily know how to read that. I do care that you could look at it, and if I asked you some questions with it in front of you, you could say, I could say, where's the biggest flux of energy bouncing back to the Earth? You could go to the 356 is away from the Earth, so it's the 333 back from the greenhouse gases. Okay? But you're probably not going to do that. But there you have it. You can see diagrams like this a lot, and they work. Now, the gases themselves, they've been a group up until this point. Now we're going to talk about different gases, because different gases are different effectiveness. And the thing that's probably not obvious to you folks is that it's a gas that absorbs a wavelength. That's right, because of its interaction with molecules. I've already said that. The most important greenhouse gas is water vapor. CO2 is rinky-dink. CO2 is present. It does work. But the champ is water vapor. There's far more water vapor than there is CO2 in the atmosphere. And you could take my word for it, and then we could skip to the next slide. But since you don't have to take my word for it yet, you don't know me that well. Here are different molecules. Here's this wavelength business. Here, the vertical graphs of each one of these are the size of it. And basically, the more color, the more important it is. They change colors. Here's our buddy CO2. Here's our buddy water vapor. A lot of water vapor trapping energy. That's the big one. CO2 traps it at these wavelengths. Ozone, O3, nitrogen oxide, methane, which you hear a lot about, hydrocarbonfluorides, and then there's another one. So the real point is that water vapor is important, and it's a part of the natural system, and water vapor is really the one. The concept that has been instilled upon, I think, many society, is that we might be able to manage this. Well, you can't because most of the CO2 goes in and out of the oceans. Now, we're adding to it. Nitrogen oxide, not so much. Ozone, not so much. CH4, methane, theoretically we might. These artificial molecules, we could easily modulate those. If you take this little rinky-dink thing out, it's not going to make much difference in the energy balance. And this is a heresy, I know, but that's okay. So it's water vapor. And water vapor is a little more complex than that, but we're going to leave it for today. All right, let's have a summary. Energy, hot, high, shorter wavelengths. The gases are the gatekeepers. The gatekeeper, it blocks some of the incoming, but it's high enough that it goes through most of it. The Earth is in balance, though, on long term. For the future, now this is, we are concerned. I mean, you can't read the newspaper without getting some article about this or methane, CH4, right? In my opinion, that's because, in theory, we can control those. We have some control over them. Well, we do have some control. We've elected to introduce them into the atmosphere with the use of fossil fuels. Can we prevent that? Can we prevent additional CO2 from going into the atmosphere? Sure. Doesn't matter. The amount that we put in so far is going to take 100,000 years to clean itself out. I'll prove that to you later in the course. But I think it gets all the press because in theory is something we could modulate. This is in my view the notion that we can maybe we've done something, we've perturbated the system, maybe we can rectify the system. And therefore you can theoretically control these emissions. But if the emissions stop and it doesn't matter the CO2 levels, really? All right. This is that. Now we're about ready to do something. We're about ready to go to a definition to set up your homework. All this was just to get you sort of worn down. Oh, we did that, okay. Anything on all that physics? We just covered a whole course of physics. Energy. To try to understand the relationship of CO2 only to the energy balance, folks have developed something called the climate sensitivity, which is the name of this module. And the climate sensitivity's working definition is this: how much the average temperature of in degrees Celsius, caveat, increased if you double CO2. Start at 100 parts per whatever, you double it to 200 parts per. Does it go up a half a degree C, 10 degrees C, or what? So it's a conceptual idea. It's buried in computer models. It's not necessarily a number that people use to estimate the future, but it's used there for convenience. It's something you can articulate to somebody. We're going to double CO2, the temperature's therefore is going to go up X amount of degrees. It's a lot easier than saying, you know, there's these constants and there's all of this other mumbo jumbo. The estimates of this number go anywhere from one and change to 5 degrees C. If we set that and think about that, that's a huge range. That means instead of going up, if one number is correct, the temperature is not only going to go up a little bit if we double CO2. 5 degrees is a lot more serious than 1 degree temperature change. The ice ages are 5 degrees temperature change. So we're talking about if these doubling of CO2, then we change the temperature of the Earth the same size as an ice age. For convenience, we typically take 3. It's not an average, it's convenience. Okay? Now, digging into this a little deeper, how do you get to this thing? It's an empirical number. People have developed different computer models. They look at the computer models and they see what if you double CO2, how much the temperature goes up. We can measure the thermometer and the CO2 levels, since the CO2 goes up, this has gone up so many parts per since 1950 or something, and the temperature's gone up so much, and you can make that correlation. Or we can use the paleo records, and we can use the changes in the past. Again, both the CO2 changes and the temperature changes, and you can do the math and make your calculations. So now we're getting back to geology finally. The questions that I'm posing to you is there's a range of possibility numbers. Which one's right? If any of them. Probably none of them. There's got to be one that's about right, although it might depend on conditions. So what should we do with this as a homework exercise? Well, that's a good question. Here's different ways to get at this estimator. This is using computer models. We have a 3.2, could go here, could go there. This is a fancier set of computer models, has a slightly different number. This is the instrument record. So this one's pretty precise because we've measured, instruments are good to measure. They only get 2. If we go to the paleo record, it seems to be a lot higher. 2 to 3.2 average is, again, significant. And then if we and then there's been a lot of efforts to try, since this is such an important number, there's a lot of efforts to try to combine them, and there's what you get there. All right. I don't know why those numbers don't agree. It's a part of a conundrum. I will offer a hypothesis. All of these numbers here assume a linear rise in both the CO2 and the temperature. And over the last 50 years, there has been, basically. These, I don't know how work. There's too much math in it for these. These I'm familiar with at some level. These are dealing with temperature ranges that are more extreme than this one is. Therefore, maybe that's why the estimators are so much higher. Or, since what we're talking about is an average, and it's one thing if the temperature goes up like that, but what happens if the temperature goes up like that? And you take the average of that. You get a higher number for your average than you should, because it's a threshold system. That's my opinion of a way that these things give us so much noise. People striving to figure this out. And I'm not the first one to come up with the idea that it's because you're looking at systems that aren't, it's the wrong metric for that system. That's my opinion, but it's something to do. How many people have heard of the concept of uncertainty? Not a lot. Okay, but enough. Well, so this is good. Let's start forging new ground. What we saw in that last graph was a central estimate, a number, but there were numbers on either side. Anytime you make a physical measurement so far in science, the number isn't exactly 12 inches. It's 12 inches, possibly a little more, possibly a little less. It's the possibly a little more and possibly a little less that's the uncertainty. These things, these graphs, these are quite different in the end, because the average is quite different, 50% different. The ranges are quite different. There are overlapping estimates, depending on these two techniques, but they really give you different numbers. But the uncertainty makes it kind of all a wash, or it could be a wash. We don't know. So what's the significance of the uncertainty here? That's actually a sort of rhetorical question. If somebody were to ask me, it would probably help them with an assignment. Because there may be something on the assignment that has a question that looks an awful lot like it. But since nobody's asked me, I can't offer anything. There's uncertainties left. How do we deal with this kind of thing? All right, I'm about winding down, so just hold your breath a few more minutes and I'll be out of here. Oh look, a homework exercise. These are posted as a series of assignments on Canvas. They I ask you to fill in a few sentence textual response. We will give you a number score on that, and then we'll make a general comment on it. And the questions, to be sure they're skewed a little bit. I'd like you to go figure out, I want you to get some numbers on these concepts. So what is the global temperature, average global temperature in the year 1950? It's a convenient time, almost 75 years ago. How much was the CO2 levels? And then using the concept of climate sensitivity, find those levels there. This is working the definition. What was the level today? If we assume that the same CO2 is going to go up, if we double CO2, what would be when would that happen? It's not a linear function, but we're going to assume it for the sake of this exercise, so you don't have to get into a quadratic equation, which I'm sure you'll be happy not to have to deal with a quadratic equation. To demonstrate that there's some sort of average temperature then of the Earth, B, at this hypothetical 70 years down the road or whenever it is. How much warmer would it be if all of this concept works? The bonus question is, this kind of conflicts with what a lot of I've been saying here. This is the way that if climate were not a nonlinear system, this would be a straightforward exercise. I'm asking you to think about whether we should, as a bonus, whether we should be using something that we know has some problems with it. Pick them on. We're going to ask for these back like in the morning before class so that we have a chance to evaluate them. This one will be 20 points. The next exercise will be 30 points and then 50 or something. They keep scaling up. The first couple in exercise go up and the other ones don't. And let's see, I think I might have a couple more slides and I'll release you. To set it up, I'm going to talk more about the ice ages. This is the graph that we saw here. 65 million years of cooling and falling CO2 levels. But the details are more complex and interesting. We've changed the geometry of the ocean in the last 65 million years ago, which has put ice sheets on the poles. We're going to focus a little bit on the Quaternary because it's the last set of ice ages. They come and go like a yo-yo. Call them the ice age cycles. And then just as you may or may not be aware, sort of 23,000 years ago, the ice sheet was up in churn. The ice mass that covered most of North America was treading here, and this I can bring in spruce logs if you'd like me to from that was trapped 23,000 years ago. Okay, that gets us there. I don't think that's just a summary slide. Blah, 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 blah. The nonlinear concept, take that home. Energy, greenhouse effect. We introduced it with most of you. Climate sensitivity is a way to give a number to that. It's a good point for discussion. Let's not take it too faithfully. And the sad news, if I'm right about the system being nonlinear, then make it a matter of diddly if we stop CO2 emissions. Because we're already committed. That's not a funsy kind of concept, but you're going to hear it again. What can I answer any questions? We'll see you Thursday. Yes, sir. The question was, do you have access to this slide deck? Yes.
And as we get more lectures, I'll upload them before class, so you guys can bring them here.
And Liz is the webmaster here. I don't know exactly where she's uploading it to. And you'll have access to the video. The video will be uploaded in a couple hours. There'll be a link in Canvas. It's going to end up on YouTube. Okay, see you folks Thursday. An hour and 11 minutes, wow. How are you today?
I'm good. First, sorry about the lateness today.
Okay,
Because I
no
can't really find the track.